Hello. In this video, we are going to discuss the topic friction. Friction, as you know, is a form of force. And what kind of force? Well, it occurs between two surfaces which tend to be in relative motion with one another, that is experienced when they are in relative motion with one another. And not only that, even at rest, but in order to experience friction, you need to apply, or you need to be in contact with the object and uh, consider the force that you are applying, and then you can experience the backward force which is tending to stop it. In fact, as I speak right now, uh, I wouldn't have been able to say friction had there been no friction, because the tongue just rubs against the upper part of the mouth, and that is what enables you to speak properly. Without that, just imagine only air would pass through your mouth. This is what happens when you do not use the friction that is available inside your mouth. But that does not make sense. Well, now the concepts that have led to understanding this thing have varied across you know ages. Now, in early days, the general idea that persists till date even, is that when you have two surfaces, so this is the one of the surface which is placed on top of, and these are the micro level irregularities. Now, the surface may appear polished, or at least uh, smooth, but at the micro level you have these irregularities. Now, these are the irregularities that I have represented here, and this can be in the in the micro scale, just like in case of your hands, in the palm of your hands. Now, they do not offer that kind of friction, but at least you are holding objects, and that friction, that it is friction which enables you to hold those objects. And it is because of the irregularities in your palm, the ridges that have been formed due to the formations of the skin, that allows you to hold objects. Now, suppose this is one of the surface, and it is placed atop another surface which also has a few bit of irregularities in it at the micro level, or even in macro level. But these are the irregularities. That's a pretty uh, big one in terms of the irregularities concerned. And these are the irregularities. Now, imagine if I am moving, if I'm trying to move one surface, one of the objects, the top object, over this lower surface, this surface over here. What happens is that, as you can see, or you can predict, is that there will be interlocking in some places. As these irregularities tend to move along, these ridges, so-called ridges that are there, they will tend to get interlocked. So there will be interlocking, and this interlocking hinders the motion of one object over the other, and that results in this frictional force. Well, this is an old theory, or the general theory associated with friction. But what's new, or uh, an updated part of it, an updated theory? Well, the new concept, or the new theory that we can associate, is it is observed. And how does this new theory come into picture is what I'm going to discuss now. It has been observed that highly polished surface, such as you can take two glass blocks, and what you do is you place one glass block, the glass blocks that are used in those experiments up front in the optics experiments in your laboratories. So these are two glass blocks, and highly polished glass blocks. And when you would tend to move one over the other, what you would experience is that these two blocks will be in complete disagreement for any kind of relative motion. And you usually experience that when you tend to strike a dot on a carom board, and without using the powder, of course, a newly freshly polished carom board, and you try and strike the dot with the striker, they hardly tend to move because of the, even though the surface is completely polished. And that brings us to the new theory. What happens is that with these two surfaces completely in contact, now these two surfaces are completely in contact, as you can see. There's no gap, there are no irregularities, or irregularities are reduced to the minimum. And there will be molecules, and these are almost like molecules for two glass blocks, or even for two even for the board and the dot, in case of carom boards. So these molecules on the surface, they will be really close to one another. They are the molecules of two separate objects, but they will be absolutely close to one another. These are the surface molecules. Now again, let me remind you, I am giving you a highly magnified view of what goes on. And these molecules, as they remain on the surface, if in case they are like molecules, what happens is that they tend to form a bond because of the pressure. Now obviously, when you have placed one block over the other, then there will be some pressure which will be acting along the downward direction, and this pressure causes the molecules to come close to one another a bit further. And with no irregularities, with complete access to the closeness that is there, then they tend to form a bond. This is cohesive in nature. Cohesive forces, cohesive means for the same type of materials. In case of any different kind of material which attaches to objects, we know it is the adhesive force. So the adhesive force is not the case over here. This is the cohesive force. And this cohesive force, because of the formation of the bonds over there, they will they will uh, they will make the contact, keep it strong. And as a result of that, this relative motion, any form of relative motion which you intend to make, that is obstructed, and thus you can say that you have a greater obstruction, which is in turn a frictional force that is involved in this case. Now this actually gives us the idea that the greater the actual area of contact, the greater the frictional force. Now in the previous case, if you look at this one, the old theory that I had, the figure that I had considered over there, the irregularities were fine, the interlocking was okay with the explanation of the obstruction caused in relative motion. But even though, if there was no such interlocking that is being seen over there, in case there is no interlocking, there is a chance that this object in the upper object may just slide along its path, and no such greater obstruction is provided in its motion, or it experiences no such greater obstruction in its motion. But what about this case? Well, in this case, what you have is that because these surfaces are so close to one another, they although in this case the area may seem to be from this end, let the end be A and this end be B. So from this end to this end, although it may seem that it is completely in contact, but that is not the case, because the actual area of contact is somewhere missing because of the irregularities. But here, with no irregularities, you have the actual area to be greater, actual area of contact to be greater. And because of that, what happens is that the bonding of the molecules is the probability of the bonding of molecules becomes greater, and as a result of that, this frictional force is experienced to a greater degree or extent. So this is how we have the concepts that are associated with the frictional force. And remember, the frictional force is a non-conservative in nature. Well, what do you mean by the non-conservative forces? Well, the non-conservative means that it is path dependent. Path dependent means it depends on the path along which the frictional force acts. That which does not depend on the path, that which is path independent, is a conservative force, and you have the potential energy to be associated with such conservative force. But this is a non-conservative in nature, so the potential energy that is generally associated with the conservative force cannot be used in this case. Okay, now moving over, uh, how do we experience the frictional force? Well, we can just draw a case, and from that we can consider a graphical explanation which will help us to understand the nature of the frictional force. Now, this is supposedly a block, and this block is acted upon by an external force from that direction, as you see. And until and unless this block was acted upon by some force, you wouldn't really experience any kind of friction that is associated with it, because uh, it was idle, and you weren't applying any force to experience any obstruction along the other direction, that is along this direction, along the surface. You weren't really experiencing anything. So until and unless you do not experience, you cannot um, explain the degree of frictional force that is acting upon the object. So one must apply a certain force in order to experience the frictional force. So as we applied this external force, we experienced a frictional force along that direction. Let that be in small f, while this is in caps. Now, considering the graphical analysis for this, what we obtain, or what we achieve in this case, is that let this be the frictional force, and the applied force, which is acting independently, the friction which is depending here on the applied force. And then what we get is, as we increase the force, the frictional force increases linearly. The external force, the frictional force is directly proportional to the applied force, external force. And finally what we come up or we end up with is that a graph of this nature. This has a lot of meaning to it. Now in this segment, let me name those points. This is starting from the origin at O, and we reach a point A, and then this point B, gradually moving along C. C continues along that line as long as the force is acted upon. Now this OA segment is the segment where the frictional force was in the applied force was increasing, and as it increased along this line or in this direction, so did the frictional force, but the frictional force achieved a limiting condition over here. Until this time, the object was steady, stationary, static. And that is why this force of friction that is experienced when the object is a static condition, this is known as static friction, which goes on increasing to a certain value. And that value where this friction tends to drop along the line from A to B, just tends to drop along that line, that is known as the limiting friction. This is the limiting friction. And then further it drops to B, but it continues along this line BC, and that is the kinetic friction. Is the case when the object tends to move. Now in the limiting condition, what happens at the point A, that is, as the object just tends to move, it has experienced the maximum amount of frictional force, and it will no more experience a greater frictional force than that. And that is why now the object tends to move, because we have applied a force, or we are starting to apply a force which is exceeding the maximum frictional force possible. So from this point on, we will be applying a force which will be exceeding the frictional force, the maximum frictional force. And as it exceeds, the object tends to move, and as the object tends to move, the surface which was in contact with the lower surface, the surface of the object which was in contact with the lower surface, that tends to change every time. And because it changes, even if there is some bonding over here as per this new theory or anything like that, even if there is bonding, even if there is interlocking due to irregularities, that now is overcome, and these bonds or these interlockings are overcome. And then what happens is that the object, as it moves, this surface that you see, the lower part of the upper body, that goes on uh, changing every time the body moves, and the surface below also keeps on changing, so they are not in regular contact with one another. So the area of contact is now reduced every time as the object tends to move, and that is why the friction drops a bit from A towards B, drops a bit. And this drop in friction then is kept constant, because the motion, the speed, is kept constant. With a constant speed or with a uniform motion, if the object moves along that line, then the kinetic friction that is observed, that also remains constant, and thus you have a straight line along BC. So the friction there remains fixed, the force of friction. So this actually gives us quite an idea. What happens is that in this limiting condition that we have with us, that is at the point A in that graph, we can relate an equation to the frictional force. What we get at that point is that the frictional force is directly proportional to the weight of the object, weight which is given by the reaction force. Why the reaction force? Well, we'll know it a bit later, but as of now, what we can say is that this weight that was acting in the downward direction, that was causing the pressure to get built between the two surfaces, and as a result of that there was a certain interlocking or a certain molecular bonding on the surface level, and that weight is obviously represented by this reaction force, which is given back by the surface on that object. So the reaction force is a representation of exactly how much the weight of the object is acting on the surface. Take for example an inclined surface. Now in case of an inclined surface, if we have an object there, then the weight acts in this downward direction. However, as per the angle of inclination, you have a component of the weight to be acting along this direction. So if this is theta, then this is mg cos theta, and the reaction force here gives me the pressure mg cos theta is causing on that surface. So mg cos theta is given by the reaction force. That means the reaction force here tells us that it's not the entire weight but the component of weight which is applying the normal pressure on the surface, and thus is responsible for any kind of a bonding or interlocking that is to take place. So it is always the reaction force which gives us a representation of the amount of friction that is acting. So the frictional force is directly proportional to the reaction force, and as you know, the proportionality has to be compensated with a constant, and this constant here is mu. Mu being the coefficient of friction, and so F is equal to mu R. Usually R is mg, so it's even mu mg, but as you saw in this case, the mg can be mg cos theta, the component of the weight. So in that case, it will be mu times of mg cos theta in case of the inclined case. So better to represent it always in the form of R. So F is equal to mu times of R. Mu is equal to F divided by R. Now F is the frictional force, R is the reaction force, force by force. This is a dimensionless quantity, unitless and dimensionless quantity. So that's about the coefficient of friction. Now, having learned a few things about frictional force, what we can have is that if this is an object over a surface, then this is the reaction force given by the surface, and supposedly the frictional force acts along this line along the surface. Now the reaction force, let me take it to here for your understanding, but as you know why I was drawing at the center, because the center consists of the center of mass on which every force acts, every external force. So but to have a proper understanding, as the friction is acting along the surface, I cannot take it up over here. So what I did was I kept the friction along the surface, and I just took the reaction force to the bottom. But as you know, this isn't the case, because the reaction force always acts on the center of mass of the object, which is almost near the center of a regular shaped object. But to understand the vectors of forces, we have the reaction force, we have the frictional force, we will have a resultant for sure. The resultant of both these forces will be acting along this direction, let's say, and that resultant that we have over there, oops, that resultant that we have over there, that supposedly, let me name it as Fr. Fr is the resultant of the reaction force and the frictional force. Now this resultant makes a certain angle with the reaction force, and that angle is known as the angle of friction. Considering that triangle that we see over there in which the angle has been considered, we have tan of that angle, that is the tangent of that angle, to be equal to, as this is f, this must be f as well. So we have the perpendicular to be f and the base here to be equal to r. So tan theta in that case is equal to f by r, and f by r, as you have already studied, is the coefficient of friction. So we have tan theta to be numerically equal to the coefficient of friction. And now if we consider this object to be placed on an inclined plane, and this incline that we have over here, let it be inclined to, it is taken up, this surface, suppose it was movable and now it is taken up, and it is taken up to a certain point where initially this object was at rest, when the angle was less, that is, angle was supposedly 0. Then it was raised up along this line, and it was raised up to a certain point where this object just tends to move. And as it just tends to move, what you have is the limiting condition, and in the limiting condition you can apply this f by r equals mu. What you have, f is equal to mu r, that is the limiting condition that we had applied. And at this angle theta, the reaction force will be equal to mg cos theta. And we have the component of the weight to be acting along the incline, and that component being mg sine theta, while mg is acting along this direction. And this frictional force and the limiting condition that will be acting along the incline in the upward direction, and this frictional force will be numerically equal to the mg sine theta component, because this is a limiting condition, remember. And so in that case what we get is f is equal to mg sine theta, and this is obviously the limiting condition where the angle was raised to such a point. Well, let me take this as alpha for just to make a difference with this angle of friction. So let this be the angle alpha instead of theta. So this becomes alpha as well, and this becomes alpha as well. So mg sine alpha is for f, and as we know, r is equal to mg cos alpha. Now taking the ratio, what we get is f by r is equal to, the mg's can get cancelled out, sine alpha by cos alpha is obviously tan alpha. So tan alpha here is equal to f by r, but wait a minute, what is f by r? F by r is simply mu. Mu is equal to tan alpha. And so we have another relation for the coefficient of friction. Now tan alpha is equal to mu. Tan theta is equal to mu. So all we have with us is tan alpha has to be equal to tan theta, or we have alpha is equal to theta. But what is this alpha? Theta for sure is the angle of friction. But what about alpha? Alpha is known as the angle of repose. Now as the surface, you know, the angle of repose is that angle to which a horizontal surface is inclined, is raised so as to achieve the minimum or the limiting condition of the frictional force to act on a given object which is placed over it, or is the angle to which the surface is inclined such that an object placed over it just tends to move. Now the surfaces that we consider in each case, they are a pair of surfaces. So if that pairing changes, so does the coefficient of friction between them. So for different types and different materials that we consider, we will have different values of tan alpha and so we will have different values of mu. Take for example, if we place even it depends on the shape of the object. The glass blocks that we considered, if they are placed one over the other, then the bonding will cause the frictional force to be very strong. But if we are placing a glass marble over a flat surface, well, that rolls down because of its shape, the area of contact there reduces, obviously, to a greater extent, the actual area of contact, and that is why that enables it to have a lesser frictional force. And that is why we use these things called rollers to roll objects, and rolling was an easier form to move objects. Now in early days, as they started to find this, they didn't have wheels back then. What they used to do is that they used to carry objects. They understood this very well, but they didn't know the terms. They had their own terms and techniques, but definitely they were advanced in terms of innovations. uh, they had, with the resources available to them, what they did was they would put those logs of woods in a rounded shape above objects, and they would have them in plenty, and the object could easily move over these logs, and rather than just pulling the heavy object just like that over the flat ground. So this brings us to the rolling friction part. Now, till this time that we were discussing, we had considered the sliding of an object over a surface. Now we can consider the case of rolling, where an object rolls over a surface. Now these days we have tires, we have many other um, type of wheels which roll, and rolling is obviously easier than sliding an object. And why so? Because, as I discussed, in case of rolling, you have the actual area of contact to be very less actual area of contact. And also the case that in for rolling, if let's consider the case of a tire, and as this tire is pressurized, and as this tire applies the weight along that surface, there is a depression that is formed, probably along the tire, or even on the surface. And this depression, what it does is, this will cause a reaction force to act in the forward direction, right? Because the rolling takes place along this line, so this depression isn't really considered, but the depression that is left back, that causes a reaction force to act along this line, and the component of the reaction force allows, with this angle being theta, the component of the reaction force allows a further push to the tire. So that is why tires, with the pressurized tires, that is, they are preferred than logs of woods that we just considered back in the early days, for early men. Okay, so in this case, so we have the rolling friction, that is, the coefficient of rolling friction is obviously much less than that of the sliding friction, because the the uh, the frictional force on the whole is very less, because F of R is much less than F of S, that is in case of sliding. So these are some of the things that I wanted to discuss in this video related to friction. It's almost the entire topic. In case you have any more queries related to friction, you can just mail me, and we will be doing some numericals that are based on these frictional force. Remember, frictional is a necessary evil because it's a necessary evil for sure. It's necessary, but it's also is evil. Why evil? Because it causes a lot of wear and tear for the objects, in which not the case of your tongue, maybe at the micro level, I don't know, but it's a necessary evil because it causes a lot of wear and tear between the surfaces where the frictional forces act, and well, it is obviously necessary, as I said, that most of the work, that even the writing part that I'm doing right now, that requires frictional force, that requires the help of frictional force. Without friction, you cannot move from one place to another, you cannot write things. So friction is necessary, but evil because it causes wear and tear. How to reduce that evil part of it? Well, you can lubricate things, you can polish, or even you can there are a lot of other methods where you can reduce friction to a greater extent. So that's all from this video. Till next time, thank you for watching.